For this lecture, I'll be sharing some data-driven workflows that I typically use when I do research and other data-driven projects. The first workflow is the School of Data's data pipeline. The School of Data is a global network of data literacy practitioners composed of organizations and individuals who are committed to advancing data literacy in civil society. And the data pipeline is their approach to working with data from beginning to end. The second workflow is related to the data pipeline, particularly expounding on the steps clean, analyze, and present. This workflow is from Hadley Wickham's book entitled R for Data Science. Hadley Wickham is a statistician from New Zealand and chief scientist at RStudio Incorporated. He is best known for his development of open source software for the R statistical programming language for data visualization, including ggplot2, and other tidyverse packages, which support a tidy data approach to data science. The first step of any project is to define the main problem that you're trying to solve or question that you're trying to answer. At this stage, you might already have a general theme in mind, so you'll want to narrow it down to one or a few more specific questions. It's also best to formulate your question in a way that already hints at what kind of data will be needed. Once you have defined your question, you must use the tools and techniques available to you to find the data that you need. For example, you might use open data portals or submit a Freedom of Information request to a specific government agency. It also helps to ask within your social networks or maximize the use of search engine tools, such as Google search operators. Sometimes though, the data you have in mind might not be easily available, so it will be helpful to know what other data can be used as proxy indicators. Once you've found feasible data sources, the next step would be to get the data from its initial location and import it into your computer for processing. This can be as simple as downloading the data from government websites and online portals. It might require more work, such as crowdsourcing data through online forms or collecting data from actual surveys on the ground as well. Before moving on to the next step in the workflow, let's talk about machine-readable data. Machine-readable data, or computer-readable data, is data in a format that can be processed by a computer, such as CSV, XLS, JSON, and XML files. Machine-readable data must be structured data. Human-readable data, on the other hand, is data in a format that can be conveniently read by a human being. Some human-readable formats, such as PDF, are not machine-readable, as they are not structured data. Non-digital material, such as printed or handwritten documents, is by its non-digital nature not machine-readable. But even digital material is not always machine-readable. For example, a PDF document containing tables of data are digital but not machine-readable because a computer would struggle to access the tabular information, even though these are very human-readable. The equivalent tables in a format such as a spreadsheet would then become machine-readable. Okay, now that you have the data, it's important to verify the data. This means checking the attached metadata. Metadata is data that provides information about other data. In other words, it is data about data. Datasets often have metadata on how and by whom the data were collected, how the dataset was organized and processed, as well as descriptions of the different variables and how to interpret them. You'll also need to check for the ownership and for any licenses and permissions to use and redistribute the data. Metadata is important in verifying the reliability and usefulness of the data. It is also generally a good practice to attach your own metadata to whatever datasets you've produced or processed so that others can also verify your data. The data that you have can often be raw or messy. For example, you can have duplicated rows or observations, column names or variables that don't match the records, and values which contain characters that cannot be easily parsed. So at this point, you can use tools at your disposal in order to render the data into not just machine-readable formats, but also into a tidy dataset. Data processing commonly occurs in stages, so the quote-unquote processed data from one stage may still be considered raw data in the next stage. As researchers, we want to clean the raw data to correct for errors, account for outliers, and transform the data in order to produce information that will be meaningful for our actual analysis. So what does it mean for data to be tidy? According to Hadley Wickham, The concept of tidy data means storing data in a consistent form that matches the semantics of the dataset with the way that it is stored. In brief, when your data is tidy, each variable will have its own column, each observation must have its own row, and each value must have its own cell. Tidy data is important because the consistent structure lets us focus on gaining insights and answering questions using the data rather than struggling to parse the data. Datasets may also have different structures. Cross-sectional data involves collecting observations on many subjects, such as individuals, firms, countries, or regions, at one point in time. This is useful if we will have no regard to differences in time for our analysis, and instead focus on differences among selected subjects. Time series data are data points that are indexed or listed in time order. This means that observations are taken at successive, equally spaced points in time. This is useful if our analysis takes differences over time for one subject as primary interest, for example, in forecasting. Panel data combines both cross-sectional and time series data ideas in that they contain multidimensional data involving measurements over time. Panel data is most useful when looking at how several or many subjects might change across time. Finally, pooled cross-sectional data across time differs from panel data because while panel data deals with observations on the same subjects in different times, pooled cross-sectional data across time observes different subjects in different time periods. Having all these in mind, cleaning or processing our data will often involve transforming the data, and this includes narrowing in on observations of interest, creating new variables that are functions of existing variables, and calculating a set of summary statistics. Going through all of these steps will allow us to effectively analyze the data. It is in this step where we want to gain insights and generate knowledge relevant to the problem we defined in the very beginning. This means that we will use skills, primarily mathematical, statistical, and other domain-specific skills to dig into the data. We can use visualizations and models as complementary tools to answer our questions. For the cleaning and analyzing steps, it's important to take advantage of different tools that can help us deal with the data. This means utilizing spreadsheet processors such as Microsoft Excel or Google Sheets, statistical suites such as Stata and SPSS, and programming languages such as Python and R. Earlier, we mentioned the complementary tools of visualization and modeling in analyzing our data. Visualization allows us to find unexpected insights or raise new questions about the data. These might give us hints that we might want to ask different questions or use a different dataset instead. However, visualization is fundamentally a human activity, so it doesn't really scale well. Modeling allows us to answer questions with more precision. Models are fundamentally computational, which means that they generally scale well. However, every model will depend on assumptions, and by nature, a model cannot question its own assumptions. Again, we can utilize both visualizations and models as complementary tools in refining our analysis. The final step in our workflow is to present or communicate your analysis. Remember to think of your target audience, make clear references to your original research question or policy question, and select the appropriate medium to effectively convey your message and insights. At this point, I'll be demonstrating how a researcher or policymaker might incorporate data into their own workflow. For the purposes of this demo, I'll be using the R programming language. R is a programming language and free software environment for statistical computing and graphics supported by the R Core team and the R Foundation for Statistical Computing. The R language is widely used among statisticians and data miners for developing statistical software and data analysis. I prefer using R because it's free, meaning users are allowed to run the software for any purpose, as well as to study, change, and distribute it, and any adapted versions as well. So aside from being accessible at zero cost, there's also a large community of users that you will be able to consult through online forums, as well as a plethora of paid and free resources that you can tap into for domain-specific applications. I prefer using R over Python, for example, which is also a free programming language. Because while Python is more general purpose, R is primarily developed by and for statisticians. So it has a broad selection of packages available to you for your statistics or data-driven purposes. To download R, just go to cran.r-projects.org and select the appropriate installer for your operating system. It's also advisable to use an integrated development environment or IDE, which will help better edit and preview your code. For this, I recommend also downloading and installing RStudio. Once you've installed R and RStudio, which are both free, the program will already come with plenty of built-in functions. But once we dive deeper into more complex and sophisticated projects, we will want to install more packages. Packages can be installed on your computer using the install.packages function and loaded using the library function. One package I highly recommend is the tidyverse set of packages. So we won't dive too deeply into R, but I would recommend using the available online resources, which are free and quite beginner-friendly. I'll be including some links and references here. Alright, let's get into using our data-driven workflow. We'll be using a very simple example that will provide an overview of how to apply what we just learned. First, let's define our question. Let's say that our general policy is poverty alleviation. Let's also say that we will already know that we want to distribute cash transfers as a poverty alleviation measure. We can narrow it down to very specific questions such as who do we expect to benefit from these cash transfers? And how much resources will we have to allocate to fund these transfers? Notice that there are certain questions that we won't be answering for this exercise, but which might be relevant for other research projects, such as are cash transfers even effective? Next, we need to find the data. If we do some research, we will find that the Department of Social Welfare and Development, or DSWD, is the agency which implements the country's conditional cash transfer program, and it uses data from the National Household Targeting System. However, we probably do not have direct access to this dataset. So what can we do? Well, we know that since we're implementing a policy for poverty alleviation, we want to get data on impoverished and low-income households. The Philippine Statistics Authority, or PSA, conducts the Family Income and Expenditure Survey, or FIES, every 3 years. And the FIES results provides data on family income and expenditure, which include, among others, levels of consumption by item of expenditure, as well as sources of income in cash and in kind. This data would be perfect for our purpose. In general, the PSA is a good primary source of economic and social data. For example, the PSA publishes quarterly macroeconomic indicators, such as the national accounts and labor statistics. Other macroeconomic and fiscal data can also be found with other departments, such as the Bangko Sentral ng Pilipinas, the Department of Finance, and the Department of Budget and Management. For micro-level or household data, the PSA is the go-to source. They conduct surveys such as the Family Income and Expenditure Survey, or FIES, the Labor Force Survey, or the LFS, the Annual Poverty Indicator Survey, or APIS, the National Demographic Household Health Survey, or NDHS, and the Functional Literacy and Mass Media Survey, or FLEMS, as well as the Annual Survey of Philippine Business and Industry, the ASPBI, and other surveys as well. Other government agencies also conduct specialized surveys and generate their own data sets. The Department of Agriculture has a registry system for basic sectors in agriculture, or RSBSA. The Department of Science and Technology conducts a national nutrition survey. And the DSWD has its National Household Targeting System. Most of these surveys or microdata are accessible via Freedom of Information request as public use or PUF files, which can be converted to more readable formats. Okay, so now we're ready to go through a demonstration of using R in our data-driven workflows, in particular for social and economic policy making. So I have here my RStudio open, and we have an R document, or an R Markdown document rather. So R Markdown documents are very useful for showing our code and outputting the results of our code chunks, but at the same time, they can produce nicely formatted documents such as HTML files. An example of an output of an R document or R Markdown documents are here. So you can see we have very nicely formatted text, but at the same time, we have our highlighted R code chunks and the results here. So we'll go through this R Markdown document together. So the first step of our data-driven workflow is to find, get, and verify our data. So for our example, we're going to be using regional and provincial poverty incidence data, which can be downloaded from the PSA's OpenStat platform. So I'll show you where we got the data. It's from this website right here. I've attached the link in your modules. And as you can see, there's an about table, so we can see footnotes, caveats, where the data came from. So this is part of the verifying the information of the data. So we can see that the data source is the PSA's Poverty and Human Development Statistics Division, and the raw data were collected from the 2015 and 2018 Family Income and Expenditure Surveys, or FIES. For this example, we're going to be primarily looking at poverty incidence among families measured in percent. And the data includes both the point estimates as well as 90% confidence intervals for each region and province in the Philippines for the years 2015 and 2018. Finally, we have to make sure that we look at the footnotes and caveats of our data, which are shown here. Our footnotes tell us that the estimates for some provinces were derived with small sample sizes and or high coefficients of variation. So we take note of this information. Now, the next step is to clean the data. Before we can import the data into our studio, we first load the necessary packages into R. So we can use the library function to load tidyverse. So tidyverse is not a single package, but a set of packages which are useful for importing, tidying, wrangling, transforming, and visualizing datasets in R. It will allow us to use the pipe operator here, which will make our code more readable. So let's now import our data. You can download the data as CSV or comma-separated value files, and we can import these into R using the read_CSV function. We can use the assignment operator here, which looks like a left-pointing arrow, to name the dataset when we load it into R. Each dataset can be previewed by simply typing and running the name of the dataset, while the view function is useful for viewing the entire dataset. Before importing the .csv files directly into R, it might be useful to preview the data first. So let's open each file in a spreadsheet editor like Excel, and you can see that our data are on the third row. So that means that as we load our data, we need to skip the first two rows in order for the data to be loaded properly. Furthermore, most of our data are numerical, but there are some missing values or missing data, which take on the values of two dots or two periods. If we don't indicate which values will represent missing values, then the entire dataset will be loaded as characters or strings, rather than as numeric. So this is the code that we have here. We use the read_CSV function. We skip two rows, and we indicate that our NA or missing data will be indicated by the two periods. And here, this is the result of our data. All right. Another useful function in cleaning of the data would be to look at some summary statistics as well. So a quick method to do this would be to use the summary function. So this will show us the data type or class of each variable. And for numerical data, it will provide the minimum, maximum, mean, median, first and third quartiles, and other useful measures as well. Once we've imported our data, the next step is to tidy and transform our data. Now we have an idea of what the data looks like. One important step is to make sure that the variable names or column headers are adequately descriptive, while also being easily accessible. Opening the .csv file shows that there are several variable names or column headers which contain white spaces, as well as special characters such as slash, percent, parentheses, and we want to avoid variable names with white spaces or special characters, as these will require enclosing variable names and backticks when we access them later. So we can use the rename function to change our variable names to a format we like. So here's what it looks like. We again use our assignment operator, and we rename the variables that we want. So for example, instead of region province with a slash, we rename it to geolocation. Poverty incidence, we replace the spaces, for example, with underscores, and we shorten the names to make it more accessible. Now, since these two datasets are related, we can actually use the full join function to merge them. So full join will merge these two datasets based on uniquely identifying keys. So both datasets have a geolocation variable, which will be used as the key to join them together. Again, every time we do this, we're using the assignment operator to name the new dataset that we are creating. Another step in tidying the data is ensuring that the unit of analysis for the data are uniform and relevant to us. Currently, the data contains national and regional poverty statistics. So for this exercise, we want to narrow this down using the filter function. We note that geolocation values, which represent provinces, begin with 4 periods, as you can see here. CAR, or Cordillera Administrative Region, starts with 2 periods, but the province Abra begins with 4 periods, and so does Apayao, Benguet, Ifugao, etc. And the Philippines has no periods in the beginning. So we can use several functions like filtering and using str_detect or string detect to filter out the geolocation data, which includes only provinces. So we can combine these functions together. Furthermore, the mutate function can be used to generate new variables and transform existing variables. So combining mutate with other functions can also help us to further clean up the geolocation variable. So for example, we might want to remove all the period characters now that we've filtered out our provinces using string remove all. We want to remove footnote indicators. As you can see in the data, there are some footnote indicators indicated by a letter like A, B, C, and a slash. And then we also want to remove any white spaces. So white spaces in front or at the end of our geolocation variables. And we want to, for example, add an NCR tag to the provinces labeled first, second, third, and fourth districts of NCR here. So we can use functions like string remove all, string trim, and string detect, as well as combining it with the case when function. So once we've done this, we can also again preview our dataset to see that it's much cleaner now. Finally, we can further transform our dataset by generating new variables from the existing ones. For example, we can create rank and percentile rank variables using the min_rank and %_rank functions. Here's the code, we run it, and it will provide us with new variables of poverty rank and poverty percentile ranks. So we have to note that the generated rank variable, when we run our code, it combines the min_rank functions and the descending function, or DESC, so that the poorest or highest poverty rate provinces will be counted as first, and the second poorest will be counted as second, and so on. For the percentile variable, the way we interpret it is the nth percentile province is poorer than n% of the rest of the other provinces. By identifying the provinces with the highest poverty rates, we can be more strategic in targeting anti-poverty and social protection measures. So now let's visualize the data. This is our last step in our data-driven workflow. Visualizations are an effective way of communicating insights to policymakers, stakeholders, and other human beings in general. From the Tidyverse, we can use the ggplot package, which is already loaded as we loaded Tidyverse, and it provides a very elegant and useful plotting function in R. So for example, here is a plot of the 20 provinces with the highest poverty rates in 2018, including the 90% confidence intervals. You can see the results here. And in general, when we're using our Markdown documents, we can knit them using this button here, knit to HTML, for example. And the results will be shown here. So these are documents will help us, our Markdown documents will help us to document the processes that we did in cleaning our data, the code that we used, and the results. So it will make it easier to reproduce whatever data-driven workflows that we have done. Once we've provided these are Markdown documents, we can then send them to the people that we want to communicate our results to. And ideally, they will be able to use our code they will be able to use our data and reproduce the results that we found. So that was a quick tutorial or quick demonstration on how we can use R to incorporate our data-driven workflows. Thank you very much. All right. At this point, we have a good overview of how to incorporate data into our research and policymaking processes. The general steps of the data pipeline are define, find, get, verify, clean, analyze, and present our data. We can use programs like R to load, process, and analyze our data. This has been quite a brief discussion, but hopefully you are better equipped and more motivated to use data to answer various questions, as well as to formulate and evaluate the policies at hand. Thank you very much.